All right, so we're going to do higher order derivatives. Today, we've talked about velocity fairly extensively. We talked about velocity as being the instantaneous rate of change. Our second derivative would be the rate of change of the rate of change. So how fast is something changing? That we're going to call our acceleration. Little side note there, remember velocity would be maybe meters per second. Our acceleration would be meters per second, or meters per second squared. So it's always good to be able to indicate what we're working with, especially with our word problems, or our relative word problems there. So meters per second is velocity, meters per second squared is acceleration. The third derivative would be the derivative of the acceleration, or the rate of change of the acceleration, or the rate of change of the rate of change of the velocity. Not a lot of application at this point for the third derivative. They are examining it and they're working with it, but not a whole lot. And we're not going to do a whole lot with third derivative, but we do anyway call it the jerk. And that's going to give us our third derivative. If we were to have a units on that, it would be meters per second cubed. A little bit of notation. We've seen the first derivative as f prime of x. We can also write that as dy dx, which means the derivative of y with respect of x. Now if I take the second derivative, we're going to put another little dash up there with the prime. So we're going to say f double prime of x, or we can say d squared y over dx squared. Not a typo there. We're going to square the d in the numerator and the x in the denominator. So this tells us the second derivative of y with respect to x. And third derivative, we can put three little primes up there, or d to the third y over dx to the third. We can also see the notation as f and then parentheses, a superscripted 3x. Fourth derivative, same thing. We could see this as four little primes, which gets to be a lot. Normally, we're going to see that as an f to the fourth, and then x, and the fourth is going to be in parentheses. It doesn't mean we're raising it to the fourth power. It means we're taking the fourth derivative. So what does this look like as we take these multiple derivatives? So we're going to do, to be able to find the second, third, fourth, we got to find the first derivative first. So derivative, we're going to do power rule here. 3x to the fourth gives us 12x to the third. Remember, multiply the 4 to the 3, decrease your exponent by 1. Derivative of negative 5x to the third is negative 15x squared. Derivative of 2x squared is 4x. Derivative of x is 1. Derivative of negative 2 would be 0. Second derivative, our acceleration. We're going to take derivative, so we get 36x squared minus 30x plus 4. Third derivative, we're going to take derivative of the second derivative. So we get 72x minus 30. And then fourth derivative, we get 72. And if we wanted, the fifth derivative would be 0, 6 would be 0, so on and so forth. A couple of things that I'd like for you to notice, that if you haven't noticed them already, as we take the next derivative, we decrease the degree of the polynomial. So we had 12x to the third. We had a cubic up here. We started out with a quartic. Taking derivative, we ended up with cubic. Derivative of cubic was a quadratic. Quadratic goes to linear. Linear goes to a constant. And then we stay at a constant, which would be 0. And this is the way any polynomial is going to work. We'll see that relationship between the exponents decreasing. Now, not going to happen when we look at a quotient rule or a product rule. Hey, that looks like fun, doesn't it? So let's go ahead and find the second derivative of x plus 2 over x minus 1. So first thing we're going to do is find the first derivative. First derivative tells us, well, we have quotient rule. We have low, d high, less, high, d low, divided by the denominator squared. We go. Cleaning up our numerator, our x's are going to cancel. We have x minus x. We have negative 1 minus 2 gives us a negative 3 over x minus 1 squared. That gives us our first derivative. In order to find the second derivative, we're going to find the derivative of this rational. A couple ways you can do that. We could do quotient rule again, or since there's no variables near the top, I like to bring that x minus 1 squared to the numerator. So I'm going to rewrite it as negative 3 times x minus 1 to the negative second. Excuse me. So second derivative is going to look, so we have a chain rule. We have negative 2 times 3. Negative 3 gives us 6. Inside stays the same to the negative third, then derivative of the function, which gives us 1. So now we can take that negative exponent, we can take it to the denominator, make it nice and clean and pretty, and we get 6 over x minus 1 to the third. And that's our second derivative. Here we have a product rule with our second derivative. Notice we have 2x squared times 3x plus 2 to the second. So derivative here, first derivative first, product rule. We have 2x squared. Derivative, we have a chain rule, so we're going to bring the exponent to the front. The function's going to stay the same. Decrease the exponent by 1 times the derivative of the function, which is 3. To that, we're going to add our 3x plus 2 to the second, and then derivative of 2x squared, which is 4x. At this point, there's a lot of things you can do with it. Personally, doesn't matter to me how you do them. What I see with this, I see a 3x plus 2 in common. So I'm going to pull that out to start with. You could also pull out a 2 and an x. Again, that's quite up to you if we want to look at that factored form. But if I do, then I'm going to end up with a 6 here, and 2 that I'm going to add a 3x plus 2 times 2. I took a 2x out of the 4x, leaves me with a 2 there. So it's going to leave me with a 6x plus 4. So I've got 2x, 3x plus 2, and then 10 plus 6x. This I don't like. We have three terms that we're multiplying together. All of them have x's in them. We have 2x, 3x plus 2, and a 10 minus 6x. I would prefer to have it down to, at maximum, 2 quantities with a variable in it so that I can use a nice clean product rule. If you wanted to multiply this completely out, I would say go ahead and do it. Doesn't matter to me, because eventually we're going to get down to a nice polynomial. So what I'm going to do is combine these two first terms into 6x squared plus a 4x. And that's times a 10 plus 6x. Again, if you wanted to multiply this out, you could. I've got it down to 2 things being multiplied together. So I'm going to use a product rule myself. Product rule tells me again 6x squared plus 4x. Derivative of 10 plus 6x, which is 6. To that, I'm going to add my second. And then derivative of the first, which is 12x plus 4. Now I can go ahead and clean this up. I'm going to multiply my 6 through. So I get 36x squared plus a 24x. Over here, I get 120 x's. I get 40, multiply my 10 through, multiply my 6 through, I get 72x squareds plus 24x. Go ahead and combine like terms. 36 and 72 gives me 108 x squareds. I have 24 and 24 x's, that's 48. And added to that, I get 168 x's plus my 40. We could factor this, we could play with it. Again, getting to the answer that's multiple choice is really what we're looking for. So I would leave it as that form at this point in time. So where are we going to see this? What are we going to do with this? Well, here's an application for our second derivative. If a ball is thrown straight up with a strictly horizontal tailwind of sustained velocity into the air from the roof of a building, the height of the ball is given to us as a function. So f sub t is going to be negative 16t squared plus 24t plus 40, where s is measured in feet and t in seconds. Can we find the velocity and acceleration of the ball 2 seconds after it is thrown into the air? So to answer A, it's asking us to find the velocity. Remember, velocity is the derivative of the position. The derivative of the position here in this case is negative 32t plus 24. So I can find v of 2 by plugging my 2 in. I get negative 64 plus 24, or a negative 40 feet per second. To find my acceleration, a of t, we are going to find the derivative of the velocity, so that's v prime, or we can say the second derivative of position. So the derivative here in this case is negative 32. If I find the acceleration at time 2, plugging in my 2 for time, I get negative 32 feet per second, or second squared. In order to answer B, I want to know what the velocity and acceleration of the ball at the instant the ball is striking the ground. So I first want to figure out when that ball is going to strike the ground. So I can find that by setting my distance, my height, equal to 0. So you have 16t squared plus 24t plus 40. Doesn't matter to me how you solve this. I see a quadratic in it, and I see I can divide out. Looks like I can divide out a negative 8, can't I? So I get 2t squared minus 3t, and then minus 5. That, my friends, looks factorable. So we get 2t and we get t. We have a minus 5 and a plus 1. Multiplying those together, I get negative 5t. Positive 2t gives me negative 3t. So setting those equal to 0, I end up with t equals 5 halves from my first quantity here, and t equals a negative 1 from my second quantity. The negative 8 is just a constant. We don't have any any variable with it, so it's not going to give us any critical numbers there. Likewise, or in addition, t equals negative 1. That shouldn't make sense to us because t is talking about time. We can't have a negative 1 seconds that we're throwing it into the air. So we know that t equals 5 halves is when that ball is going to strike the ground. If we were to look at the graph of that, we would look something like this. There's our negative 1, and there's our 5 halves. So it looks like the ball was thrown from this height and then down. So we can go ahead and find that velocity at 5 halves and the acceleration at 5 halves as well. At this point, I would go ahead and throw it into the calculator if you want. So our velocity, we get negative 32 times 5 halves plus 24. That's going to give us a negative 16. So negative 80 plus 24. What's that? Negative 66 feet per second. And then a of 5 halves, well, the nice thing is there's no variable there, so that's just going to be negative 32 feet per second squared. And that gives you kind of an application of where we would use the second derivative. Good luck with your higher order derivatives. Good luck throwing in that quotient in the product rule and finding the derivative the second time. They're fun.